There are a total of n courses that you have to take, labeled from 0 to n-1. So every course has a label, which is an integer. Some courses have prerequisite. The prerequisite is expressed in a pair. So 0, 1, it means 0 depends on 1. So the number on the left depends on the number on the right. Course 0 depends on course 1. If you have not finished course 1, you cannot take course 0. Input has two elements. The first element is an integer, which means the total number of courses. So 2 means we have course 0 and course 1. If this number is 5, that means we have course 0, 1, 2, 3, and 4. The second element is a 2D array, aka array of arrays, which has a bunch of pairs. Each of these pairs has a length of 2, so the number on the left depends on the number on the right. Course 1 depends on course 0. Course 0 does not depend on anything, so 0 can be completed and 1 can be completed, so all the courses can be completed. Return true. Now in this case, 1 depends on 0, 0 depends on 1. There is a circular dependency. You cannot complete all the courses, so return false. There are no duplicate edges in the input prerequisite. So you will not have 1, 0 appear twice in the input. Pause the video and see if you can solve it. Two test cases. The first test case has total number of courses as 4. I'll be representing each course as a circle. I'll also use the term node or vertex. They mean the same thing. Each of these circles represent a course. So 4 courses, 0, 1, 2, 3. The prerequisite pairs has 3 arrays. The first one, 0, 1, 2, means course 1 depends on course 2, meaning you can only complete course 2, then you can complete course 1. I draw an edge. Each prerequisite, I'll call it an edge. 2 depend on 3, so you can only go from 3 to 2. 3 depend on 1. We have identified a circular dependency, so this should be false. Second test case, same thing for nodes or 4 vertices or 4 courses. 0 depend on 1, you can only go from 1 to 0. 0 depend on 2, 1 depend on 3, 2 depend on 3. This is fine. There is no circular dependency, so true. I hope by now you understand what the question is asking. The question is asking cycle detection in a directed graph. Now, what is a graph? The graph data structure is described as each node or each vertex has a label, which is the node value. This has a node 0. And the graph also has a neighbors array. Now this 0 does not have a neighbors array. For this 3, the node value is 3. The neighbor array has the node 2 inside. For this 3, node value is 3. Neighbors array has 1 and 2. We can represent the graph data structure using a 2D array. We can use the index of the array to represent the label of the graph. So this is the index. The index is the same as the label. So when we refer to the index, we know which vertex we are referring to. Initially, the graph is empty. We are adding neighbors to the array. For example, 0 does not have any neighbors. 1 has a neighbor, which is 3. 2 has neighbor, which is 1. 3 has neighbor, which is 2. In this graph, 0 does not have neighbors. 1 has neighbor, which is 0. 2 has neighbor, which is 0. 3 has neighbor, which is 1 and 2. You can think of neighbors as from 1, you can go to 3, because you can visit your neighbors. It is directed graph because you can go from 1 to 3, but you cannot go from 3 to 1. Same thing here, 2 can go visit 1, but 1 cannot visit back. Similarly, for this node 3, you can go to your neighbors, which is 1 and 2. So the graph has indices where the index represent the graph label. And the element that is stored at those indices are the neighbors. You can go visit your neighbors. You can think of neighbors as adjacent elements, the elements that you can visit through the edge. So all these elements are edges if we use graph terminology. So how shall we solve the problem? The algorithm is called topological sorting. There are two ways to do topological sorting: breadth-first search and depth-first search. The breadth-first search version is called Kahn algorithm. The depth-first search does not have a name. I will do both of them. I'll start off with the breadth-first search version, which is also called Kahn's algorithm. Breadth-first search requires a queue. We will push all the nodes that does not have any more dependencies onto the queue. Can you tell me, in this graph, what are the number of dependencies of all the nodes? We know there's 0 dependency on node of 0. There's 1 dependency on 1, which is 2, because 1 requires 2. There's 1 dependency on 3, because 3 requires 1. And there's 1 dependency on 2, because 2 requires 3. So we can build a dependency array. There are many names that you can call the dependency array. For example, degrees or ranks. So 0 does not have dependency. All the rest has dependency of 1. For this graph, 0 has 2 dependency, 1 has 1, 2 has 1, 3 does not have dependency. So for the first graph, who shall we push onto the queue initially? 0, right? Because 0 does not have any dependency. We can think of the queue as the node that can be readily fulfilled, or the courses that can readily be finished. Because if you do not have any dependency, I can finish you immediately. That's why I push you onto the queue. Because 1, 2, and 3 still have dependency left, you are not yet ready to be finished. We will also have a counter, let's call it cleared. Initially, it is 0 because we have cleared 0 courses. At the end of the operation, if the counter is 4, it means we have cleared all the courses. Okay, so the queue initially has 1 node, which is 0, because it is the only node without any dependency. So we can clear it, because we can clear a node without dependency. So cleared equals to 1. We go visit the neighbors. Does 0 have any neighbors? No. We can access 0's neighbors from graph 0, right? This is an array, which is this guy. The neighbors is empty, so we do nothing. Then we go back to the queue. The queue is empty. End of operation. We have only cleared 1 node. Because 1 is less than 4, we have failed to clear all the courses. And it makes sense because this 2, 1, and 3 has a cycle. Now let us look at the other graph. In the second graph, who are the nodes that have 0 dependency? It's 3, right? Because 0. So we push 3 onto the front of the queue and cleared counter is 0. Now because 3 have no dependency left, we have cleared it, right? Cleared is 1. Now we go visit the neighbors of 3. How do we go visit the neighbors of 3? Graph 3. So neighbors of 3 give us 1 and 2. Now we will reduce the dependency of 1 and 2 by 1. Why is that? Because previously 1 has 1 dependency. 1's dependency is 3. And now I have completed 3, so 1's dependency should drop by 1. You can also think of 1's degree should drop by 1, or 1's rank should drop by 1. Whatever it is, 1's will drop by 1, which is 0. And now we see, does 1 have any dependency left? No, right? Because 1's dependency is 0 now. So we can push you onto the front of the queue. We do the same thing to 2 because our neighbor has 1 and 2. We just finished 1. Let's look at 2. We drop 2's dependency count by 1. Why? Because 2 previously has 1 dependency, right? It's here. 3 is your dependency. I have cleared 3, so 2's dependency should drop by 1. 2 drop by 1. You can also say 2's rank drop by 1. You can also say 2's degree drop by 1, whatever. Now 2's dependency is 0 now. We can push it to the queue, right? Because our queue is for the nodes with 0 dependency. Now 2 go to the queue. Okay, now we go to the front of the queue, which is 1. 1 has 0 dependency. We can clear it, right? So clear becomes 2. We go visit the neighbors of 1. How do we go visit the neighbors of 1? By doing graph of 1. What is graph of 1? Which is 0. 1 can go visit 0. We drop 0's dependency count by 1. Why? Because 0 depends on 1, and once 1 is cleared, 0's dependency should drop by 1, right? So 0's dependency originally is 2, now drop 1, so it's 1 now. Now, does 0 still have dependency? Yeah, it still has 1 dependency, right? So you are not ready to be on the queue yet. Does 1 still have any neighbors? No, it only has a neighbor of 0. Okay. Then we go back to the queue, we go to 2, because 2 is the front of the queue. 2 does not have any dependency, so we clear 2, so cleared equals to 3 now. Now we go to visit the neighbors of 2. What is the neighbor of 2? Which is graph of 2. Okay, what is the graph of 2? 0, right? So we go visit 0. 0 drop dependency count by 1, or drop degree, drop rank by 1. Because 0 depends on 2. Now 0 count will drop to 0. Because 0 does not have any more dependency left, 0 is ready to be pushed onto the queue, right? Now at the front of the queue, 0 has no dependency left. Why? Because 0 here has no dependency left. You can clear it. So cleared equals to 4. Then you go visit 0's neighbors. What is the 0's neighbors? Graph 0, right? What is graph 0? This guy. Graph 0 is empty, so nothing to be done. We go back. The queue is empty. End of operation. Because the cleared variable equals to 4, which is n. N is here, right? Cleared equals to n. That means we have cleared all the nodes. We return true. Now let us code it out. We need a graph, which is an array of arrays. How do we create a 2D array? Copy paste code from Stack Overflow. Array, this will be num courses. This will be a array. Now for const, prerequisite will be, let's say, uv of prerequisite. Now u depend on v, so in order to build u, you have to do v first. So the direction is from v to u. So graph v dot push u. We also have a rank will be array num courses dot fill in a 0. Now ranks u plus plus, right? Because u is the node that is dependent. Just log it and see if it makes sense. I have used this test case. Makes sense, right? It's the same as this test case on the left. For, this is the same. Now graph will be empty 0, 0, 1, 2, and my rank is 2, 1, 1, 0. Let's get rid of the log. Initialize the queue. Push nodes with no dependency, or rank 0 to the queue, right? So ranks dot for each r and I, where I is the index. Index is synonymous with the node label. If r is 0, right? If the rank is 0, we will in queue dot push we push the node, which is synonymous with the rank, right? Then we will do the proper BFS, aka Kahn's algorithm. BFS is always a while loop while q.length, right? We will have a counter, which is called clear, but we can do it the opposite way. We do what is the front of the queue, which is q.shift. Whenever we pop an element from the front of the queue, we will do minus minus num courses. I'm just doing the opposite of clear plus plus, right? In the end, return. If we cleared everything, that means num courses become 0, right? This is the same as, originally our cleared equals to n, where n is num courses, aka total number of nodes. Then here we still do the same thing, push nodes with no dependency to the queue, but before that, reduce neighbor rank by 1, right? So what is our neighbor? Is the graph of f. Graph of f dot for each, because our neighbor is an array, right? Neighbor, right? Neighbor. So ranks of the neighbors will minus 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 if the ranks is 0, right? If it is 0, we will incube, right? Q dot push nay. Now, if you want to be fancy, you can put pre-increment here. It must be pre-increment, because pre-increment evaluates this thing, then returns the value that is evaluated. So let's test it out. It's expand. True. Let me submit. There we go. What is the time complexity? Assuming we use a notation where V is num courses and E is the length of prerequisite, aka ages. Num courses is actually our vertices or nodes, and prerequisite is actually the number of ages. What is the time complexity? It should be upper bound by this function, right? In this function, we have a graph f dot for each. What is our graph? Graph is this 2D array. For every element, we need to go visit all its neighbors. So element 0, we go visit neighbors. Element 1, we go visit neighbors. Same for 2 and 3. What is the total number of neighbors? It's the total number of edges. What is the total number of edges? It's the prerequisite length, which is E. So all the neighbors is E. The graph has a length of V. So total time complexity is V plus E. In this graph, V plus E is 8. In this graph, V is 4, E is 3, so it is 7. Go to Wikipedia. Runtime is all of V plus E. The video is running too long, so I will not be introducing depth first search in this video.